Hi, Assalamualaikum and a very good morning. So now we are in a new chapter, which is chapter 2, Atomic Structure. In this chapter, there are going to be three subtopics altogether, which is 2.1 Bohr's Atomic Model, 2.2 Quantum Mechanical Model, and subtopic 2.3 Electronic Configuration. In this video, we're going to focus on the subtopic of 2.1 Bohr's Atomic Model, part 1 of the video first. So in this video, we're going to learn on how to describe the Bohr's atomic model. Also, we're going to look into the explanation of the existence of energy level in an atom. Next, we're going to do the calculation regarding the energy of an electron, where we're going to use the formula given here. Also, we're also going to calculate the energy change. So here is energy, and here is energy change. So there must be a delta E here. Okay, so a triangle which represent delta, and this happening during a transition. Last but not least, we're going to calculate the photon of energy emitted by an electron that produces a particular wavelength during a transition. So this is also a formula given here. So this is covered in part 1 of the video, which is in this video. For the subtopic of T, we're going to look into that in the next video, which is part 2. So without any further ado, let us start with part 1 of the video first. So Bohr's atomic model. So Bohr's atomic model are basically proposed by a Dutch physicist known as the Niels Bohr. And according to him, this model is only works for a one electron system. For example, hydrogen atom. So you know that hydrogen will have one proton and one proton, zero neutron, and have also one electron. So as long as the atoms or the ions have one electron, then this system will work for the Bohr's atomic model. And according to him, the Bohr's atomic model will work according to four postulates or four theories. For the theory number 1, it stated that the electron will move in a circular orbit around the nucleus. And when moving in the orbit, the electron does not radiate, dia tidak akan membebaskan, and at the same time, it will not absorb any energy. And as mentioned, it only works for a hydrogen atom, for example, as long as it is in one electron system, hanya ada satu electron. And as what you can see here, this circling around here is known as N. Okay, so the first level, the first orbit next to the nucleus is N equal to 1. The next one is N equal to 2. And the next one, the pink color, is N equal to 3, and so on and so forth. So the N here can be called as orbit, or they can be called as a principal quantum number, or they can also be called as energy level or shell. Okay, so that's for postulate number 1. For postulate number 2, Bohr stated that the energy of an electron in a hydrogen atom is being quantized. That is, an electron moving in an orbit can only have a certain amount of energy. By means of that, when the electron is at energy level of N equal to 1, for example, it will possess a certain amount of energy. When the electron is at N equal to 2, it will have a certain amount of energy. So the energy is specific to each level. Okay, and this is calculated according to the formula given here, which is En equal to negative RH times 1 over N squared. So when your N, when the electron is at N equal to 1, then you will substitute 1 here. If N is equal to 2, means that the electron at here, okay, then N here gonna be 2 squared. Okay, you will learn more about this later. Next, we move on to the next postulate, which is postulate number 3. So according to him, at ordinary condition, the electron is at the ground state, which is at the lowest level. But when the energy is being supplied, the electron will absorb the energy, and this is going to be promoted to a higher energy level, in which in this case is N equal to 1 to N equal to 3. And this process is known as excitation. Okay, And this will bring us to the fourth postulate, which is postulate number 4. So when the electron is being excited, then it is very unstable. The electron is very unstable. So the electron will fall back to a lower energy level, and this in this case from n equal to 3 to n equal to 1, and this process here will release a specific amount of energy in the form of light, or known as photon. And this process here is known as emission. And when we are talking about emission, this is something that interesting to us as a chemist. So we, at least at this for this chapter, we're going to focus very much on emission because it gives us the information on the photon part. And as what you can see here, the energy of the photon, which is, you know, that photon here in the form of light, where you have learned in physics that delta E is equal to hv, and the energy of the photon that's being released will equal to the energy difference between the energy level. So delta E of the photon is given here, and delta E of a different energy level is given as here. And as what you can see, delta E is equal to hv. At the same time, delta E is equal to this term here. So you can conclude that delta E is equal to this term, and this also equal to hv here, where h is a Planck constant and v is a frequency. You will learn more about this in a later slide. Okay, so for now we have completed these 4 postulates. Next, we're going to look into the energy level diagram for the hydrogen atom. So what is an energy level diagram? So energy level diagram is basically a representation as what you can look here. So it consists of a potential energy, and it also consists of an energy level n equal to 0 up to until infinity. And this is constructed based on the Bohr's atomic model that we have learned. So as what you can see here, and if you were to look it closely, you can see that the energy gap between n equal to 1 to the nucleus is very huge. Jarak dia adalah jauh. And this is consistent to what you're going to see in the energy level diagram here. So the distance going to be huge as well. But when you go from n equal to 1 and to n equal to 2, the gap will be smaller. Jarak dia adalah semakin dekat. And if you will look into n equal to 3 and n equal to 2 to n equal to 3, the gap will be even smaller. And same goes to here, the gap going to be even smaller. And if you were to repeat that up to more energy level, you will get it to be even smaller, even smaller, even smaller, even smaller, until you cannot see the energy gap between the energy level. And when you cannot see the energy level between two orbits, you can say that it has reached infinity. And this infinity is also known as the convergence limit. Okay, convergence limit. And at convergence limit, there's gonna be no force of attraction between electrons to the center of the nucleus. Okay, and as I have mentioned just now, the diagram should be consistent to what you see with the energy level diagram. So let's say I have an electron from the orbit n equal to 1. So when the electron absorb energy, you can say that the electron going to be excited to a new higher level, which is n equal to 3. Okay, and this going to say that the electron is going to be excited to a higher energy level, which is from n equal to 1 to n equal to 3. And at n equal to 3, the electron become unstable. So the electron going to fall back to a lower energy level, for example, n equal to 3 and to n equal to 1, and you know that the energy is being released. Okay, and this process is known as emission, and as a result, they're gonna produce a photon. And this photon here will have the energy equal to hv. Okay, so the diagram here is consistent on both the energy energy level diagram and the Bohr's atomic model. Of course, it is up to you whether if you don't want to start from 0, you can also start from n equal to 1 and n equal to 2, and it's basically up to you as long as the gap is there's going to be a difference in gap between from one stage to another. Okay, and later you're going to learn that there's no it is not necessary for the electron to start from n equal to 1. It can also start from n equal to 2 up to n equal to 5, and then it can fall back to n equal to 1. Okay, so you're going to learn more about that in the next subtopic. Okay, now we're going to go back into the energy of an electron, where we have talked about this based on the postulate number 2. So the energy of an electron going to be given as in the formula here. So the En is equal to negative RH times 1 over n squared, where RH here refers to a Rydberg constant, and it carries a value of 2.18 times 10 to the power of negative 18 joules. Meanwhile, the n here refers to a principal quantum number, or you can call it a shell, energy level, or orbit. And n here can be an integer value, which is 1, 2, and 3, depending on where the electron is being located. If the electron is located at n equal to 1, then you can substitute 1 into this equation. Okay. Also, the energy can be 0 if the electron is located infinitely far from the nucleus. As mentioned, if the electron is being far away from the nucleus, it means that the electron will not experience a force of attraction. Dia tidak akan dapat daya tarikan daripada nucleus, and as a result, the energy gonna be 0. And because of this, the forces of attraction are taken to be negative, because you know that the proton in the nucleus will carry a positive charge and the electron going to carry a negative charge. So we usually denote the change, the energy of attraction or the force of attraction in a negative value. Okay, so do not worry that too much because you just follow it in the formula here, which have a negative sign here. Next, I have talked about what we are interested in our postulate number 4, which is we are interested in the emission. So, as mentioned, radiant energy or a photon can be emitted when the electron moves from a higher energy state to a lower energy state, and it is given by the difference in energy between the energy level. So, there's going to be a change in the energy level from a final state minus the initial state. So this is our initial state pada permulaan, and this is our final. Okay, and the change is denoted by final energy minus initial energy. And you know that from the previous equation, En is equal to negative RH 1 over n squared. So we can say that when the energy at initial state, it is equal to Ei equal to negative RH times 1 over ni square. And when it is at final state, we can substitute n with final, and negative RH still maintain, and 1 over nf square. And as what you can see here, EF, we can substitute this term here. So EF is equal to negative RH bracket 1 over nf square bracket minus here refers to minus here, and Ei refers to this term here, which is negative RH 1 over ni square. And if we were to expand this bracket here, you're going to get negative RH 1 over nf square plus RH 1 over ni square. Okay, and if we were to rearrange RH, we're going to take out, okay, and because it is in positive 1 over ni square minus 1 over nf square. So at last, you're going to straight away using this formula here. The derivation is not required for your level, but I'm just showing that so that you can see a connection. Why this formula, where is this formula coming from? So you just remember if I F, I minus F, and do not forget the square here. Okay, and you know that because we are moving from a high energy state to a lower energy state, so you know that the energy level of Ni gonna be higher than F. Example 3 into 1. And remember, the RH here is equal to 2.18 times 10 to the power of negative 8 joule, similar to before. Also, when you're talking about photon, we know that the photon itself will carry an energy, which is delta E is equal to hv, where h here refers to a Planck's constant, in which you're going to have this value here, which is 6.6256 times 10 to the power of negative 34 joule second. And V here refers to a frequency, or we call it as mu. Okay, so the frequency will have a unit of per second or hertz. And the frequency here can also be written in form of c over lambda, where c here refers to the speed of light and lambda here refers to wavelength. Okay, and as you know that delta E is equal to hv, and V here refers to c over lambda. So we can substitute that V is equal to c over lambda, and at last we're going to get hc over lambda here. And as mentioned, hc over lambda here can also be equated with the delta E that we have learned in this previous slide. Okay, so to learn more about that, let us look into the example. So for example 1, we have to calculate the energy of an electron in the second energy level of a hydrogen atom. So the diagram, you can imagine it to be something like this, where the electron going to be situated at the n is equal to 2. And for this reason, you're going to use the formula of En is equal to negative RH 1 over n squared. So RH here refers to a Rydberg constant, and it has the value of 2.18 times 10 to the power of negative 18 joules. So you're going to plug in the value of the negative 2.18 times 10 to the power of negative 18 joules, multiply by 1 over, because since n is at the second energy level, so it's going to be n squared. Okay, and do not forget the negative sign, and we can say that once we do the math, we're going to get equal to negative 5.45 times 10 to the power negative 19 joules. So the energy unit is going to be in joules, because the joules come from the Rydberg constant here. For example 2, a photon with a wavelength of 7.19 nanometer are emitted. So you know that in an energy level diagram, a transition from one higher energy level to a lower energy level going to release a photon, and this photon here will produce a wavelength which is 7.719 nanometer, and we have to calculate the energy difference in joules. And next, how about the energy difference for 1 mole of electron of a similar transition in kilojoule per mole? Okay, and for the energy difference, we're going to use delta E is equal to hc over lambda. Okay, and lambda here we have 719, and you need to be very careful because nanometer here refers to 719 times 10 to the power of negative 9 meters. Okay, and some of you will straight away use 719 in the equation, but you have to expand it into like this. Okay, so your h here refers to a Planck constant, which is 6.6256 times 10 to the power of negative 34 joule second. And then your c here will refer to the speed of light, which is 3 times 10 to the power of 8 meter per second. And then your lambda here going to be 719 times 10 to the power of negative 9 meter. And as what you can see here, I wrote down the unit so that I know meter and meter going to be cancelled out, second and per second going to be cancelled out, and joules is my final unit, which is consistent to the change in energy. So once you do the maths, you're going to get 2.765 times 10 to the power of negative 19 joules, which is in joules. Okay, and as mentioned, some of you will make a mistake of writing 719 only without times 10 of negative 9. So be really careful of this. Okay, and for the next question, we need to find the energy difference for 1 mole of electron in kilojoule per mole. So in order to find the energy difference for 1 mole of electron, it's basically the same thing, which is delta E, which is gotten from this part here, which is 2.765 times 10 to the power of negative 19 joules, but we need to multiply it by per mole. So Na here, because we are referring to 1 mole, so it refers to our Avogadro's constant, which is 6.02 times 10 to the power of 23 mole negative 1. So our Ea here is going to be 2.675 gotten from here, and Na, which is 6.02 times 10 to the power of negative times 10 to the power of 23 per mole. So once you do the maths, you're going to get the answer of 166,453 joule per mole. But the question asks you in kilojoule per mole. So from joules, you need to convert that into kilojoule. So you need to divide that by 1000. So 1, 2, 3, and 4. Sorry, 1, 2, and 3, because what 3 is 0. You're going to get 166.4 kilojoule per mole. Okay. And for our last question here, which is example 3, is the energy change during the transition. Mesti ada pergerakan elektron daripada energy level yang tinggi kepada yang rendah. So, for example 3a, we need to calculate the energy change in joules that occurs when an electron falls from n equal to 5 to n equal to 3 in a hydrogen atom. So you can imagine it to be something like this, where the electron fall from n equal to 5 to n equal to 3. And we are talking about transition. We need to use the formula of delta A is equal to RH 1 over Ni square minus 1 over Nf square, because it involves transition, the energy movement, the electron movement from n equal to 5 to n equal to 3. Okay, so RH here, you just plug in the value of 2.18 times 10 to the power of negative 18 joules. Your initial, if, mula daripada yang besar kepada yang kecil. Initial to final. So your initial is 5 square and your final going to be 3 square. Okay, so don't forget the square here. And then once you do the maths, you're going to get negative 155 times 10 to the power of negative 19 joules. As mentioned, the negative sign here is just to show that the energy being released during the emission processes. You can also put it as 1.55 times 10 to the power of negative joule release. Okay, and from the delta E here, you can relate that to with frequency as well as wavelength. And for this reason, we're going to use delta E is equal to HV. Our delta E here is obtained from up here. And delta E here, we can take it without a negative sign because frequency cannot be negative. So we just take the magnitude. Okay, we just take the value without the negative sign. Okay, without negative sign, because frequency cannot be negative, and same goes to wavelength. So delta E, we just take it 1.55 times 10 to the power of negative 19, and our H here refers to the Planck constant, and then we need to find frequency. So as mentioned, joule and joule can be cancelled out, and as a result, your frequency is equal to 1.55 times 10 to the power of negative 19 joules divided by 6.625 6 times 10 to the power of negative 34. Joules per joules can be cancelled out, and once you do the maths, you're gonna get 2.34 times 10 to the power of 14 per second. Okay, and you know that the frequency can also be related with a wavelength. So lambda is equal to C over V, and C here refers to a speed of light, which is 3 times 10 to the power of 8 meter per second. And then your frequency you gotten from here, which is 2.34 times 10 to the power of 14 per second. So per second and per second can be cancelled out. And at last, you're going to get the units of meter here. Okay. And once you settle the maths, you're going to get 1.28 times 10 to the power of negative 6. And the question asks here in nanometer, which is in times 10 to the power of negative 9. So to convert 10 to the power of negative 6 to 10 to the power of negative 9, we need to bring it by 3. Okay, so it's going to be 1280 times 10 to the power of negative 9 meter, or here you can change it to 1280 nanometer. Okay, so I think that's all for today's video. See you again some other time. Bye.